Special relativity. Table of contents, special relativity. Starting with Galilean transformations, sort of a precursor to this whole topic, then Einstein's postulates, simultaneity, relativity of time, relativity of length, the Lorentz transformation, and finishing off with relativistic momentum and energy. Galilean transformations. In order to describe where something is or its motion, you need to relate it to something else. That's the purpose of a reference frame. Choose a coordinate system in space and make measurements relative to the system. There is no one preferred reference frame, and frequently there is a need to translate measurements made in one frame to another. One reference frame can even be moving relative to the other. As long as the frames move with a constant velocity, that's key, zero acceleration, relative to each other, we can use a Galilean transformation. Accelerating reference frames are the province of general relativity and won't be covered in this course. Before the math is done, think about different reference frames. If you're sitting in a bus that is going 25 meters per second, which is roughly 56 miles per hour, the person sitting next to you, relative to a reference frame that has you at the origin, is not changing his position, and his speed relative to you is 0 meters per second. If someone is standing at a bus stop relative to a reference system that has her at the origin, the person in the bus is moving at 25 meters per second and is getting farther away from her. And if a bus is moving parallel to your bus with the same velocity, a person in that bus would agree with you. Your seatmate looks stationary. Who is correct? Why, you all are. Let's start by choosing a two-dimensional reference frame based on Cartesian coordinates. That's the old XY stuff that hopefully you're familiar with. We'll only be solving problems in one dimension though. The stationary frame, over here in black and marked with an S, is not moving. Then choose the M, a moving system, that's in red, over here, and put it in motion with a constant velocity, and we'll call that velocity u, and that is the velocity of the M system with respect to the S system in the x direction. And let's take an event over here. The coordinates of that in the xy system will be x comma y. All right, so we'll draw a little arrow to that. In the x prime system, the system that is moving, the coordinates will be x prime and y prime. So let me delete the marks here and just pause on this and check it out and make sure you follow everybody on this slide. Now let's add a bus and we'll attach that to the M frame, the moving frame, this red frame right here. And we have an observer here at the stationary frame, the stationary system. The bus and the M frame is moving at a speed u with respect to the stationary observer in the S system. The bus is at rest with respect to the M frame. So as the M frame moves, the bus goes with it, and this person over here does not move. U is the relative velocity of the two frames. The observers in both frames agree on this velocity, but each will express it in the opposite direction. This is a simpler example, as only one of the reference frames is moving. Okay, we're keeping this frame stationary and moving the M frame. One more thing now. We're going to add a person within the bus. And that person moves at a velocity v sub m relative to the bus, because this person is in the moving frame. The person is also moving at a velocity v sub s with respect to the stationary observer. The Galilean transformations enable the calculation of the position, velocity, and acceleration of the person in both frames, the stationary frame and the moving frame. This only works for inertial reference frames. Both frames need to be inertial. That is, they are moving at constant velocities, zero acceleration. All these motion parameters are vectors. Since we're only working in one direction, vectors to the left will make them negative, and vectors to the right will be positive. And here are the transformations. First, the Galilean position transformation comes from the second kinematics equation, and A is equal to 0. right? Because neither one of these frames has an acceleration. It's going to be x is x prime plus ut. So x is what this person is measuring. X prime is measured by someone in the bus. U is the velocity of the moving reference frame, which in this case is the bus. So x is the position of the bus rider in the stationary frame. Just saying it again. X prime is the position of the bus rider in the moving frame. The velocity transformation is v sub s is v sub m plus u. Vs is the velocity of the bus rider in the stationary frame, and Vm is the velocity of the bus rider in the moving frame. And finally, the acceleration transformation, As, whatever the acceleration of this person here in the stationary frame, is exactly equal to the acceleration in the moving frame. Now I know we've been talking about A is equal to 0, right? But that only applies to the reference frames. The person here can have an acceleration, but the frames, the S frame and the M frame, must have 0 acceleration. Let's do a couple examples now. A person, right over here, is walking with the speed of 1.3 meters per second from the front of the bus to the back of the bus, and that's V sub m. The bus is moving at a speed of 22 meters per second. What speed does an observer at a street corner observe for the person in the bus? Let's write out the givens. The person has a speed of 1.3 meters per second, but he's going from the front of the bus to the back of the bus. So that's going to be a negative velocity. So V sub n is minus 1.3 meters per second. U is the velocity of the bus, and the bus is to the right, so that's positive. We use the Galilean transformation for velocity, which is V sub s is equal to V sub m plus u. Use a negative value for V sub m since the person in the bus is moving to the left. We substitute in our givens, and the observer here, the stationary observer, sees the person moving at 20.7 meters per second to the right, which is a bit slower than the bus. Why? Because the person is moving opposite the direction of the bus's motion. Example 2. A person is sitting in a bus moving at a speed of 16 meters per second. The person is sitting in a position of 4.2 meters from the back of the bus. Right, so this distance here, according to the person, is 4.2 meters from the back. The back of the bus passes an observer sitting on a park bench at t equals 0 seconds. After 5 seconds, at what position does the observer see the bus rider? The givens are the speed of the bus, which is u, the position of the person relative to the bus. So the person right here is at 4.2 meters from the back of the bus, and that's in the moving reference system. And time is equal to 5 seconds. Find x, which is the position that this person sees the bus rider at. Use the Galilean transformation for position. X is equal to x prime plus ut. Use a positive value for x prime since the person in the bus is in front of the back of the bus. Here's our equation. X prime, this is the position of the person relative to the moving reference system. Here's the velocity of the reference system m, which is where the bus is tied to. Here's our elapsed time. And we find that after 5 seconds, this person observes the bus rider 84.2 meters away. The bus rider relative to the bus is still at position x prime equals 4.2 meters.